Welcome to BTEC Revision. In today's lesson, we're looking at Kirchhoff's laws. By the end, we should be able to calculate the current or voltage in circuits using Kirchhoff's laws. How does current behave in a junction? This is given by Kirchhoff's first law, which is stating the total current entering a junction is equal to the total current leaving a junction. And this can be given by the equation below. Here, I stands for current, and we have in, which stands for going into the junction. So the current going into the junction equals the paths of current leaving the junction, so I1 plus I2 plus so on, until you reach the last path. Here is a diagram that can help us understand this a little bit better. Here we have I in, and that's going into the junction over here. We'll label that as J. And then we should have the current leaving the junction at I1, I2, and I3. So if we add the currents for I1, I2, and I3, that should be equal to I in. So for our case, the equation is going to become I in equals I1 plus I2 plus I3. And we could label these values. Let's say I in is 10 amps and I1 is, let's say, 5 amps and I2 is 2 amps. Plugging this into our equation, Kirchhoff's first law, the values we have here are 10 amps equals 5 amps plus 2 amps plus I3. Rearranging for I3 and collecting like terms, that gives us 10 amps, take away 5 amps, take away 2 amps, which is equal to 3 amps. Therefore, I3 is equal to 3 amps. So this law, Kirchhoff's law, first name Gustav, was a German physicist who found two laws that we need to learn about. This is the first law on current. And this law is based upon the idea of conservation of charge, which means that no charge can be lost or created in a circuit. So if we add up all these currents, so we can put all the currents in one side. Let's choose the left side. So current in, and then we'll take away current 1, take away current 2, and so on. Therefore, the right side will be free. That's equal to 0. And we can write this in a simpler way. Here we have the letter sigma, which represents the sum. So the sum of these currents, I, if we add all these up, is equal to 0. So this is an abbreviation of this equation. Now, let's look at an example. Calculate the currents in A1, A2, and A3. Now, looking at the circuits, the longer line here be the positive, shortest line is negative. Okay, so we have a battery. And from the right side, we have 1 amp. Okay, we'll stick with the conventional current. So can start from the top right. We know that we have 1 amp of current going through the circuit, also through the battery, and it has to be traveling. According to Kirchhoff's first law, it is not going to lose any charge. You're not going to lose any charge and not going to gain any charge. So going through this ammeter, we should have 1 amp. Right. And then we reach this junction over here. And we can see going ahead, we see a 100 ohm resistor. And going down along the path below, we also have another 100 ohm resistor here. So what would happen is the currents would have to split because there's two parts. And since they are equal in resistance, they will split evenly. So therefore, the currents, half is going to go through the first path, and the other half is going to go through the second half. So the currents will go through the resistors, and the ammeters will experience half the current. So therefore, values for A2 are going to be 0.5 amps, and A3 will be also 0.5. And then At the next junction, the current is going to add up. So we'll have 1 amp going through the ammeter again. How does potential difference behave in a circuit? This is given by Kirchhoff's second law, which states that the total potential differences across the circuit loop is equal to the sum of the potential differences dropped around the loop. And this can be given by the equation V in, which stands for voltage going in to the circuit, is equal to V1, which is the voltage across one component, plus V2, voltage across the second component, plus so on until you reach the final voltage. And if you remember from a previous lesson, we know that V is equal to I times R. So each individual voltage value here, or potential difference value, we're going to use those two terms interchangeably. V1 is equal to I R1 plus I R2, and in this equation, plus so on. Now, the reason why we assume I is the same along the circuit is because we will assume a series circuit here. And looking at Kirchhoff's first law, we know the current is not going to change as it's going along in the round series circuit because it's not going to split. So it should stay the same. Okay, conservation of charge. And the resistance values are going to change, depends upon the component. They could be the same, but they could be different. So we just label them as R1 and R2. So we can also write this in a short form. The sum, if you remember this sign, sigma, sum of the potential differences. Okay, so that would be in this case, V in is equal to the sum of the potential differences dropped around the circuit. So sum I times R. And in this case, that would be V1 here and V2 over here. And this second law is based upon the law of conservation of energy, which essentially states that the energy you put into the circuit equals the energy you get out of each loop in the circuit. Now let's look at this example. Calculate the voltages V1, V2, and V3. Looking at the circuit, we have 12 volts in the battery. The current is flowing, and we have a parallel circuit. So some electrons are going to go through the first path, and the rest are going to go through the second path. So we have, following the circuit, 100 ohm resistor plus another 100 ohm resistor. Okay, and we also going down, we have a 100 ohm resistor. So in parallel, voltages are going to stay the same, okay, in a parallel circuit. So we know along this line over here, we will have 12 volts. And along this line over here, we'll also have 12 volts. Okay, so this circuit is going to gain 12 volts. And these two are going to gain 12 volts. So for V3, which is reading across this resistor, we should have 12 volts. And for V1, since the voltage is shared, it should be 6 volts. And V2, since it's equal, it'd be shared equally, should be 6 volts as well. Now pause the video here and attempt this exam question. Find the current flowing in each resistor. What we'll do for this question, since we need current, let's call it I1 here, and the second current I2, we have the resistances, but all we need is the voltages. And if we remember, the voltages are the same in parallel. So since this is a parallel connection, we can say we have 12 volts here and 12 volts here. So if you remember from a previous lesson about voltage and current, they're directly proportional to each other. So V equals I times a constant, which happens to be the resistance. So rearranging for I gives us V over R. So for the first case, I1 is equal to V1 over R1, and that's just 12 divided by 2, which gives us a value of 6 amps. And then for I2, it's V2 over R2. So V2 is the same, 12 volts, and R2 is 50, which gives us a value of 0.24 amps. And if we add these two up, we get the current in the circuit. So that will be 6.24 amps. Just be I. And that's the end of the lesson. If you would like to boost your grades, visit us at btechrevision.com, where there's lots more quiz questions and resources. See you next lesson.